Hello everyone and welcome to another episode of Data Deep. So today's video will be a continuation of the previous video wherein we started to understand the basics of language models, not large language models, but small language models. And today we are going to dial it and we will try to get closer towards understanding large language models and some extra stuff. So let us begin. Things that we are going to learn today. So, what are transformers? What is the self attention in transformers? And what are large language models? A few myth versus fact comparison for language models, large language models, and a few strategies to help us get started with large language models. So, what are transformers? So, last video we got to know the terms like encoders and decoders. So we will today we will see how these encoders and decoders come together to build up a transformer. Uh, Transformers are basically made up of stacks of encoders and decoders, and at a very basic level, uh, there are several encoders and decoders which come together to impart certain functionality to a particular transformer model depending upon the training and the training data that goes into the entire process of getting a transformer ready to perform certain tasks. This is a pictorial representation of a transformer, so you can imagine the encoders to be stacked on top of each other and the decoders in the same way stacked on top of each other. And why they are done so? Because the input from each encoder passes on to the different to the other encoder on top of that, and finally we get a particular output with respect to the encoders, and same goes for decoders. So in short, you get an input and the input gets processed further and further and further till we get our desired output. The secret sauce for the success of transformer is something known as self-attention. Now these self-attention layers are present in both the encoders as well as decoders, and they are not alone. The self-attention layer is paired with another layer which is known as feed-forward layer, but we will take a look into it later. For now on, we will concentrate on what an attention does. So let us take an example of a text. I saw a cat. It jumped over the fence. Now, you and me as a human, we know that the word "it" actually refers to the cat and not the fence. But how does the model actually understand that? This is where the self-attention layer comes into picture because it scores uh, each word in a text or in the corpus of text on which the encoder is trained on. So this self-attention layer comes into picture and scores each of the text, and it groups similar or related text together and unsimilar or unrelated text apart from each other or further away from each other. So, for example, in this particular input text, uh, the way the scoring is done by the self-attention layer for these two words, cat and it. So, if we consider a two-dimensional graphical representation, then the words cat and it would come closer together and the word fence would be further away. In this way, our model actually understands that okay, the word it and cat are related, so let us so it has more probability to come after one another rather than the word fence coming after the word cat. So the calculations appearing inside a self-attention layer is much more complex. We are not going to dive deep into that in this particular video or in this particular series, but I would leave some descriptions uh, down in this video, which would lead you to the articles which actually take you deep down into the calculations of that appears inside the self-attention layers. Now, decoders, in very simple terms, the decoder can be thought of having a dictionary sort of thing. because it is trained on a huge corpus of data, and we can call this dictionary the vocabulary of the decoder, which contains all the words that it has learned during the training phase. Now the decoder also has an attention layer, and the role of the attention layer inside a decoder is that uh, it takes in the scores and numerical representations generated by the encoder, and then that is matched with the decoder's vocabulary to predict which word comes after which word. So now it takes an input. For example, I saw a cat, it jumped over the, and now it's job to predict which word would complete that sentence. Now it takes that sentence and it compares all the words across its vocabulary, the scores generated by the encoder for each and every word in the input sequence, and tries to find out which other words in its vocabulary are closer to this input sequence, and then it finally comes up with the prediction. The calculation again in this stage is much more complex, which we won't be covered here, but you can get to know more about it from the links provided in the description section. Now let us move closer to large language models. So this infographic here is a complete roadmap of different language model till date. I mean the most popular ones till date. And you can see that things like chatbots had been there for quite a long time, but the most popular has been the chat GPT in recent years. And ChatGPT actually brought the term large language model to limelight and to the masses. So let's take a look into what they are. Now, this infographic here is a representation of the architecture of the first GPT model, GPT-1, and which was developed by OpenAI. And GPT shot into fame because it could generate human-like text when an instruction was given to it. Under the hood, GPT is made up of transformers, and they are based on, and GPT is a decoder only network, saying that it does not have an encoder, but it has only a decoder. And its architecture is very similar to the kind of architecture that I explained in the previous video and the starting of this video. Only thing missing here is the encoder, which is not present in GPT. And GPT was trained on huge amount of data over many days, and thousands of dollars of GPU hours were invested in that to make the GPT-1 model so powerful. Uh, and due to this huge amount of data, GPT has a very large vocabulary to generate human-like text. And now, in recent years, in fact, this year, OpenAI came out with their latest model GPT-4, which surpasses all the other GPT class or GPT family models. And GPT-4 has been trained on, huge amount of data, huge. It has to be precise, it has 100 trillion parameters. So you can just imagine the kind of data that it was trained on. And in simple context, that the amount of data it was trained on is internet scale. Means it's really huge, which you and me cannot possess. So huge amount of data were scrapped from the internet, and GPT-4 was trained on that. However, OpenAI has not released uh, the architecture details of GPT-4. So we don't know exactly what kind of architecture it has and how much it deviates from the earlier GPT models. Some large language models like GPT-4 are also augmented with better knowledge via fine tuning or training via training technique known as reinforcement learning via human feedback, or RLHF for short. So here GPT-4 is first trained. It is given something, it predicts some output, and a human would judge that output and give feedback to GPT-4, and it would again learn from that feedback. right? Via reinforcement learning. So this actually makes the GPT-4 model more robust and more, capable of generating human-like text. What are large language models really? Large language models at a very, very stripped down version or very basic level, they are neural networks, huge neural networks, which are fed huge training data. And then with that huge training data, mm, uh, generate some, some text given some instructions. So I would say that large language models can be considered as intelligent dictionaries which search answer from a predefined data set, that is their training data, and provide an answer to you. So here the word intelligent is used very lightly because today large language models are nowhere close to human level intelligence, unlike the popular pop culture would lead you to believe. At the very best, they dream up certain answers given an instruction or given in human inputs, that they dream up certain stuffs based on their training data, which can be factually wrong sometimes. So you must, uh, you know, you must take the generated data with a grain of salt if you are using large language model in your project. Now let us look at some myth and facts of large language models. So people say that large language models generate facts, which is wrong because the text generated by large language model is made up by the large language model with the knowledge it has from its training data, and it is more like dreaming up things which are not always fact. Large language models are solution to everything, which is again wrong because there are certain tasks which an LLM cannot do, uh, or are not practical enough, like text classification, for example. LLMs can replace small models, which is not again true because small models are still cost effective as they require lesser compute time, lesser GPU hours, and lesser resources to train and run. So for several tasks like text classifications, intent generation, etc., small models are still practical as compared to large language models. Large language model can usually shoot up your cost, your project cost, and so before uh, riding the LLM hype, you should analyze your use case if it does fit the usage of LLM or not. LLMs are AGI or artificial general intelligence. A big no, because in today's date, we are nowhere close to human intelligence with this large language models. LLMs are going to take away jobs and destroy humanity. Again, a big no, and I don't just believe this, and I won't get into explaining why this is wrong. Now, some strategies to use LLMs in your project or in your team or in your organization. So today, the top of the line LLMs like GPT-4 are really closed source. You have to pay to use them. And so here are some strategies that would effectively help you to, balance out your cost and your use case. And so the first step is to analyze first. Don't write the web, and take your time to analyze your use case. If it does require a giant model to be, I mean, if your problem statement does require a giant model, so many times the small models will just do fine for you. Always prototype, always take small models, uh, prototype the solution for a problem statement on small models, and then move on to big models. Today, there are tons of open source large language models, so you can easily use those to prototype. It gives you a fair idea about what are the shortcomings of these open source models or small models, and if it does not justify your use case, you can move on to the bigger models. So, open source large language models sometimes fit your bill. So, always prototype is that. Use techniques to adapt LLMs to your use case. Fine tune the LLM on your data that makes it more robust to your particular use case. Then use certain retrieval techniques like retrieval augmented generation, or RAG for short, to reduce the hallucinations or to reduce the generation of factually wrong things by the large language models. So we would continue this further in our next video. Till then, like, share, and subscribe. Thank you.